gonna click go live, and that should be fine. And I guess that should be it. All right, we should be live now. Okay, so let me just share my screen. And let's go here. Okay, so everybody, welcome back to chapter 13. This is week 13, and we're going to be looking at our first CNNs from scratch. So last week, what we did, we covered off convolutions, and this week, what we're going to do is we're going to build on top of that, and we're going to start doing our first convolutions, and basically we're going to start building our first CNNs from scratch. So the reason why this week is actually very exciting, and this is the week where we make a lot of progress. So we started with the journey where we didn't know what convolutions are. We pretty much used fast AI, and we used those 5 or 6 lines of code, and we didn't really build things from scratch. So from the last session, we've been going deeper and deeper into vision, and we're actually at that point where we can build our own CNNs from scratch. And what I mean by that, like, we built our very simple CNNs where we use the convolution followed by ReLU, which was the activation function. This week, what we're going to do is we're going to start wrapping up, like, we're going to get a good understanding of what more can be done. Like, we're going to start looking at batch norm. We're going to start looking at everything, pretty much wrap up chapter 13. And then next week, we're going to do ResNet. So ResNet is this, let me show you what ResNet is. So let me go, one sec, let me go to Chrome, go to my profile, and search ResNet. So ResNet is this paper, Deep Residual Learning for Image Recognition, and it's a really, really influential paper. So if I go to Semantic Scholar, by the way, if you haven't checked out what Semantic Scholar is, I would recommend now is a good time to just know what Semantic Scholar is. If you go deep learning, now if I just search paper name, then what this does is it will not only show me, like, sorry, one sec. So I can click on that paper. It will give me it will show me the title of the paper, but it will also tell me, like, how many times it has been cited, how many times it has been cited. It will show me which other papers that cite this paper. So basically, in research, citation means, like, if I reference something that's related to this paper, then I will cite it or give credit to this paper. Then this is where the idea originated from. And then 74,018 citations is a massive, massive number. So ResNet is one of those papers that has been absolutely influential in the deep learning world. And Kai-Ming He has been, Kai-Ming He, I believe, was the main author. And then what we're going to do from going forward from this week is we're going to wrap up convolutions, and then we're going to be at a point where we can start looking at this paper. So if I go and I check out the PDF of this, if I check out the PDF of ResNets, and then this is the paper that we're now at this point where we can start reading this research paper from scratch, and we can also implement this in PyTorch. So there's a lot of things that we will understand from this paper. And one thing then I do want to highlight and also point out is that if I go to community 1DB, so if you haven't looked at the 1DB forums, now is a good time. And I just want to show you particularly 2 things. So if I go into community events and I go into paper reading group, then click on this master list biweekly, which is the pinned post. You will see the upcoming paper reading sessions over here, and you will also see the past paper reading sessions. So we've looked at MData, we've looked at DATA, we've looked at KITE. So there's, like, all of these past paper reading groups that we've done in the past. And from this week, or basically from next week, we're going to start looking at ResNet in the paper reading group. So I was thinking maybe this is the perfect time for everybody in this group to transition to paper reading group as well, because you're at that point where you can start looking at papers. And I think if you need an easier way to get started with this paper, you could do it using, like, blog posts, or you could read chapter 14, and even for DenseNet, then there's blog posts for squeeze and excitation, there's blog posts for efficient nets, there's blog posts. So I think from this point on in computer vision, we can only build on top of what we know. And, like, now the like after chapter 13, the platform is set for you guys. Like this is where kind of Fastbook's jobs, like there's more concepts to learn, but this is kind of where the platform is set now for you to build things on top of. So now we can all go in our directions. We can all start learning papers. We can all start learning more about things. And in fact, what we're gonna do is from next week, we're not only going to look at ResNet, but I'm also planning on starting like some paper reading groups are bi-weekly, but I'm also planning to start like these live coding sessions where we build ResNet from scratch in PyTorch or using FastAI, and we do the same for DenseNet. So I think this is my appeal to you guys that if you have followed me with Fastbook so far, then now is a really good point to start doing these on the side as well, because this will help you in your deep learning journeys quite a bit. So that being said, again, that's something that's next week. And also next week, if we have a look at, if I go to Fastbook, so we're on chapter 13. And you'll see chapter 14 is ResNet. So next week at Weights and Biases, we're discussing the ResNet paper at the paper reading group. And we're also doing chapter 14, which is ResNet at Fastbook. So it might be a really good idea to do both of them together. And you could definitely attend the paper reading group. Coming back to this week, I really thanks everybody for giving such good feedback about our last lecture on convolutions. I really appreciate the feedback that I've received, and it's really exciting to see. I'll get back to this slide before, but it's really exciting to see all these blog posts now being written about convolutions. So Ravi Mashru has written one about convolutions in FastAI, and this is a really, really wonderful blog post. If I go to that link, 1db.me/fastbook13, that should take everybody to the week 13 discussion thread. So this is where we're going to start discussing all our threads. Somebody's already typing, which is great to see. So I can just go into this thread like this one by Angelica. She's already provided links for all the blog posts that people have written last week. So if we go to this, thread, which is 1db.me, I'll say again, 1db.me/fastbook13. This should bring you to the discussion thread. So as we keep going forward in our session today, feel free to ask me questions just at this thread. Okay, so I was coming back to the blog post of going to Ravi Mashru's blog post, which is on convolutions. You can see like there's these nice visualizations, and it's been explained on what strides are, what padding is, and it's a really, really nice blog post that contains everything. I particularly like this one by Naresh as well. So let me go back to that week 13 thread. This Naresh's blog post. I click on that, and you can see this convolution explained. And the reason why I like this, really like this, is it also explains like all these kernels that we discussed about last week. So you can see blurring effect, or you can see the box kernel. There's like all of these different kernels that you can see, Gaussian, sharpening. So there's like these different kernels that Naresh has pointed out. So I really like this, really like that blog post as well. One of my favorite ones, though, I just found about this 20 minutes ago, has been Prime Minister Modi's beard detector. So if I go to that, I'm not sure if this is here. It is not. So let me just find it on Twitter. It's this one. So let me go to this. Blog post. So what Durga has done, he did, and he's just catching up with FastAI, and it's so exciting to see that he's writing this about FastAI chapter 2. But what he's actually done is that he started with the beard detector, which was the black beards. But what he did is he got Prime Minister Modi's images from 2014, and then Prime Minister Modi's images from 2021. So you can see how the beard has grown, and it's like very different facial recognition. Like he's basically doing facial recognition, and that the beard is the difference between the two mainly. And then he's built this classifier that can classify Prime Minister Modi's beard, and it can do so with about 93% accuracy. So I really, really like this. I really enjoyed reading this blog post. And then Vinayak did a nice tweet about convolutions, and then there's another one which is by Ravi Chandra. He's also written about chapter 13, which we covered off last week. So this is really, really lovely to see all of these great blog posts that all of you have been writing week after week. again, I will say this again, this is a good time to start reading papers. This is, if you want to improve or like build on top of what we've been doing, this is a really, really good time to start learning about transformers on the side. This is a really good time to start learning about like all the basic concepts. So if you find something you don't know, this is a good time to Google it, and this is a good time to like actually spend time just trying to understand what's really going on. So one of the things I did ask, so we'll go back to the chapter 13. Let me just close all of this. So we'll go back to chapter 13, and where we finished last time was we created our simple net. So that is, so we saw like what a broken CNN is. We saw what the output shapes are. We saw what a simple CNN looked like. But one thing I did ask everybody is like to figure out why the spatial dimensions are 14 by 14 and so on. So I hope you guys spend some time on this. And we kind of wrapped up just above this. So we looked at the convolution arithmetic, but this is kind of where we stopped. So we kind of created our first very simple CNN, and now we're at that point where we can start looking at the convolutional arithmetic. So let's start here. So just give me one sec. Let me open OneNote. And I'm just going to go Fastbook, chapter 13. All right. That's where we are. Okay. So that's chapter 13. So let's start with 1.2.2, which is understanding convolutional arithmetic. So today what we're going to do is we're going to finish chapter 13 all the way till batch normalization. And I'm going to show you some parts of like the batch norm paper and how that translates into code. So I'm just going to show you some bits of what that looks like. But then we're going to actually finish off chapter 13, and then next week we're going to pick up ResNet. And then we're not left with much. We're just left with then the architecture. We're pretty much left with 4 or 5 chapters, and we're left with tabular and NLP. So that's not a lot left. Okay. Cool, a lot of talk, but now in this understanding convolutional arithmetic, basically this isn't something new. Like this is something I explained, I believe, very well last week. Is like if we have an input size, like if we have a model. Let me just rerun this whole notebook again. I hope it won't take forever. But I can just grab from my model. I can just grab the first layer, and you can see like the first layer is a convolution 2D. I'm just trying to zoom in so everybody can read this better. So then there's the first layer is a convolution 2D. The number of input channels is 1, the number of output channels is 4, and the kernel size is 3 by 3, stride 2 by 2, and padding 1 by 1. And then it's followed by a ReLU. So as it says, we have 1 input channel, 4 output channels, and a 3 by 3 kernel. I hope I don't need to explain this again, because this is something we spent a lot of time on last week. So if there's any doubts about this, just have a look at last week's YouTube. So I'm actually just gonna just very quickly run all of this. Like we know that the shape of this convolution layer is, again, this just means 4 kernels where the input channel is 1 and the spatial dimension is 3 by 3. Okay, we can see the bias because in convolution you just add the bias as well. So remember from, where was that? Remember from this, we are also adding bias terms in the end to all the convolutions. So that's just that. So because we have 4 kernels, we just add 4 biases. So that's going back to that. Sorry, that was 1.2.2, wasn't it? So 1.2.2, so you can see the bias shape is 4. So I won't spend a lot of time on 1.2.2 because again, this is something that we covered in a lot of depth last week. So starting with receptive fields. Okay, so let's say if I have my input image that looks like this, right? And then what I'm going to do, because let's say I just have a single channel input image, so the number of channels is 1, and let's say this is 2 to 4 by 2 to 4. Okay, 2 to 4 by 2 to 4. And then let's say I have a convolution kernel that is also single channel, but is 3 by 3. Now, if this convolution kernel goes all the way across my image, then what's going to happen is that my output, member, is going to be, I think it's going to be 2 to 2, right? Because it's going to skip, it's going to miss the two boundaries, it's going to miss the locations. So it's going to be 2 to 2 by 2 to 2. So what's happened is, like, starting from a bigger size image, our spatial features on when we do the first convolution are less. And then when we do the convolution filter, like these 3 points, like this point has actually, like that particular point of this second filter, this particular point has actually looked at those 9, basically those 9 coordinates in the image, right? So I think this will be much more clearer if I show you over here. Okay, so let's say this is my image. I apply my convolution filter. I get some output. So this particular pixel in my second layer has seen the 9 pixels in my first layer, correct? And then when I do a convolution after this, so my next convolution happens on this, let's say I'm going to use a different color. So let's say I'm using orange. So when I do a convolution on this, then these 9 pixels have actually seen more of the image, right? So that they've covered more of the first image. I hope this makes sense, because then when we do this, then the next spatial filter has seen like more of the first image. So basically what we have is, like, you have a first image, then you have a smaller spatial filter, and then you have a smaller spatial filter. But this output is from that much, and then when you say this output is from that much of the second layer, but all of this is actually all of that yellow region. So the point that I want to make here is that this single pixel here, let me just use a different color. So the point that I want to make here is that this single pixel here has actually seen that much of the actual image. But this particular, again, I'm going to use a different color, but so this is, again, I'm just going to call this conv0. Let's say that's my input image. I'm going to call this conv1, and I'm going to call this conv2, right? So conv2, when you do the convolutions, like when you stack convolutions more and more on top, conv2 has seen, like, has interacted, or like the calculation is done with that much of the convolution 1, that many spatial dimensions, and then similarly all of that for convolution 0. So as we keep going down deeper and deeper into the convolution, basically as we keep going down into the deeper and deeper layers, they have more context of the overall image. So when we keep going down deeper and deeper, there's going to be a point when the convolution, or basically the output activation, would have seen maybe the whole of image. So this particular idea of this way of, like, thinking of things is just called receptive field. So we just refer to this as the receptive field of the convolution kernel. So you can see there is this, if you go to the book's website, there is this Excel spreadsheet that shows the receptive field, but it is exactly what I've explained here. Is that as you go down deeper and deeper into the convolution network, it has seen more and more of the image, or like interacted with more and more of the image, or looked at more and more pixels. So that's just this basic idea of receptive field. It's not something that will, it's really handy to know, but like not knowing this would not mean that you can't train a CNN. So you can still train a CNN in case you didn't know about receptive fields, but that's just something I want to share. Another thing that this is actually an interesting one. So let me just go I just want to go at the top and see where my index is. This is acting a little weird. This should show my index. Okay, there it is. That's bad. And I'm just going to go down back to a note about Twitter. Okay. So then if there's any questions about receptive fields, let me just go back and have a look. If there's any questions about receptive fields or questions so far. This may be why do we train ResNet 50? Why do we train ResNet 50 from scratch? And why not import weights from ImageNet? Sorry, let me know if there's a lot of background noise. It's just a plane passing by. I'll just shut down the door. Just give me 1 sec. That should be better, I hope. Okay. So the question is, why do we not import weights, or why do we do this? Where are we training a ResNet 50? Like, is this for pets, or like in which context is this question from, is my question. So like, is this for pets classifier? If you could please comment and reply to this and provide me with more context. It's like we've trained ResNet 50s at a few different situations or few different cases. So where is this coming from, please? Okay, so now I'm going to go back to Twitter. Something I do want to actually talk about is, every week I show you these PowerPoint slides about like, some Niazi did a nice blog post on collaborative filtering, or Durga did a nice blog post on Prime Minister Modi's periods. But where do I actually find them? I find all of this on Twitter. So Twitter, there's a really strong ML. There's a really strong ML community on Twitter, and I pretty much use Twitter to highlight all of my work and blog posts, and that's something that's definitely worked in my favor. So I also recently gave a talk about like how to publicly share your work at Queensland AI Hub. So I can try and find the link for that and put it on the blog post. But basically, the idea is Twitter is this place where Twitter is this single place where the ML researchers are really active. You'd be surprised to see like a paper gets highlighted. For example, let's have a look at this one. There was one by Barrett Soft that he's a researcher. Yes, this one. So the way I keep up with research papers is mostly on Twitter, or the way even I ask questions is mostly on Twitter. And I learned this from Jeremy. Like, this is not something I learned on my own. This is something I picked up from Jeremy. And when I was reading Fastbook the first time, I saw this section about Twitter, and I didn't know about Twitter. Like, I didn't know like how active the machine learning community is on Twitter. And this is something I was so surprised to learn and find out, that now I'm actually using Twitter on a daily basis for at least a few minutes a day. And you can see Barrett Zoff is a senior research scientist at Google Brain, and he recently published a paper which is called I think it's called multitask, or let me just double check what that is called. It's when that opens. But the point is, like, there's this paper that tries to answer this question, which is how do we combine knowledge from multiple labeled and unlabeled data sets to train a great general model. And you can see that that's being discussed on Twitter. There's an example, there's visualizations, there's the results of that, there's what happens when you add more pseudo labels. They studied like a suite on different tasks. These are different experiments that were done, and looks like archive's down. Anyway, and then they were like this different experiment on what if they already trained the checkpoint. So the point is, like, Twitter is this, and this is as of 12 hours ago. So you can see the value. There's a lot of value in Twitter, and to be active on Twitter. So please, as you write your blog posts, use Twitter to highlight and publicly share your work. Like, use Twitter as a platform where you follow people, use Twitter as a platform where you share knowledge, and then eventually you'll see in your deep learning journeys that you'll get to a point where you're using Twitter on a daily basis to like keep up with, oh, what's new in this world. So it's even more so, like, Twitter is 90% of the updates that I find on what's going on with, say, Tim, or what's going on with research side of things is from Twitter. And in fact, I even have notifications turned on for a few people that I do have to follow on Twitter. So these are like these different things that you that you want to try? And I know I'm taking a lot of time just to talk about Twitter right now, but see, like, even this example from Jeremy. So when he was working on, Jeremy just wanted to double check, like, what was it when he wanted to basically use straight to convolutions, and he just wanted to ask that what was written in this book about straight to convolutions, was that accurate? So he pretty much asked on Twitter, is like, I forget, why did we move? Like, he basically asked the question. And then Christian Szegedy, he's the author of, I think, InceptionNet. So there we go. Christian Szegedy is the first author of Inception, and he's the 2014 ImageNet winner, and he's responding to that question. And then you can see Jan LeCun. He's definitely Jan LeCun, and he's a Turing Award winner. And we talked about him in chapter production as well. But you can see, like, all of the highly influential people are on Twitter. So if I and people who have defined kind of the way deep learning is. So if I search Jan LeCun, you can see, and there's like a lot of tweets. You can see that there's again, he retweeted something 7 hours ago, which is about rolling Facebook Pay, or like there's all of these different things that you can follow on Twitter. So I would definitely say, from this point forward, use Twitter as a platform to share your work, and use Twitter as a platform to follow other people's work. And the best way to get started with Twitter is just to follow Jeremy, and then see the people that he follows. Like, that's how I started. I just went to Jeremy's profile, and I saw, like, okay, he used to follow about 1,000 people at the time. And then I followed all of those 1,000 people. And then suddenly my homepage was full of research papers. And then as you go, you're like, okay, these particular kind of research papers are not useful to me. So you don't follow them, or you unfollow them. And like, that's how you then build your Twitter profile. So I just want to share this, share that definitely from going forward, please get more active on Twitter, because it will definitely help you. Okay, so now we're back to color images. So a color, sorry, just give me 1 sec, please. 1 sec. Okay, so now Giri just goes, I did the opposite. I followed you and Sayam first, and then onwards. I think that's also fine. Sayam and I pretty much follow, I think most of the, like, Sayam also has lists. So on Twitter, Sayam also has these machine learning lists where he's brought all of the people in the fast AI community. So he's got like these different lists that he follows. So he's got a list for, I think, researchers. He's got a list for fast AI folks. So do check that out as well. But either way should be fine to get you started. Okay, so color images. So now we're back to, like, how does this convolution, like, until now we've just looked at convolutions on single channel images. We haven't really looked at color images, or how that is different with color images. So let's do that now. So how does that look like? So we already know color images are blue, RGB basically. So let me I draw that blue. I'm going to draw a red. Just need to make that a bit thin. And finally a green. All right, so that's RGB, right? So that's my RGB image, that's my input. And now when I'm going to do a convolution, the way that convolution looks like how is that any different for a 3-channel input image versus a single channel input image? The only difference that you'll see over here, as you can see, like, every image, if you see, like, every image is basically consists of 3 channels, red, green, and blue. And then the only difference that you'll see is, like, you have now basically your kernel size. In your kernel, you just define your input number of channels is 3. So what you have, instead of having a single channel kernel, you have a 3-channel kernel. So you have 1 channel for blue, you have 1 channel for red, and you have 1 channel for green. So now, instead of, like, having a single channel kernel that we used to have, like, we used to have single channel kernel, now we have a 3 channel. So this is all, actually, I should just draw this like that. So now that becomes my kernel, okay? And what happens is, so if that's my kernel, what happens is this 3-channel kernel will again go around the 3-channel image in the similar manner as it did for a single channel image, okay? So what that means is that you have your blue channel, you have your blue kernel, and it's going to go all the way around. You have your red channel, then the red kernel is going to go all the way around. You have your green channel, and the same thing for the green kernel, okay? And then what you have, as you can see here, you get the outputs and you just add them up. So this is how you do convolution with color images. So remember this, when I have my red, basically my blue, red, and green, I can just, like, this thing is going to give me some output, this thing is going to give me some output, and the last one is also going to give me some output, right? So this is going to give me one feature map. Actually, I should just draw it with blue. So it's going to give me like a smaller blue feature map. This one is going to give me a smaller red feature map. Blue, red, green. And you basically just add them up. So you just add them up to get your final thing, your final output. So that's how, like, that's how this thing works. So let me show you, just show you an example. So if I have, say, my input, so import torch, my input is torch 1, 3, 2 to 4 by 2 to 4. That just means I have a single image, single 3-channel image of 2 to 4 by 2 to 4. I can say my conv. I should also import torch.nn, import torch.nn as nn, and I can just have nn.conv2d, and I just say my input number of channels is 1, out channels is 1, and the kernel size is 3. All right, and then I can just do conv x, and I can check my output shape. So as you can see, now the output is basically, it's one feature map because you had one input, but the number of channels in your output is 1 because we said output channels as 1. We could have also done output channels as, say, 64, in which case we would have gotten 64 channels in our output. So this is, again, very, very similar to what we did for single channel. Instead, it's just being occurred for 3 channels. So in your 3-channel, you just have a 3D kernel. So like, one of the differences that's key over here is, like, even though it's called convolution 2D. So like you will see in convolutions, you'll find 3 things. You'll find, in convolutions, you'll find conv 1D, you'll find conv 2D, conv 3D, and so on. But like right now, we're looking at this 2D conv. And what you did see over here is, like, the convolution kernel is actually 3D, right? Because it has 3 channels, red, green, and blue. So conv 2D doesn't really mean that your kernel size is 2D as well. It just means it goes in 2 dimensions. It just means it goes, so if this is my image, it just means it goes across the height and it goes across the width. So it's just, the convolution kernel is just going in towards your width and towards your height. So that's just the main difference that I did want to highlight over here. Are there any questions on convolutions? Let me just go. Oh, there's quite a few questions. Okay, let's cover these up. Okay, is conv2 uses receptive field of both conv1 and the one before that for the final convolutions? No, it's just using conv1. So I guess there's some it's unclear on what receptive fields are. So if this is my input, right? This is my input image. If I apply, let's say I apply that massive convolution kernel on, like, this is, say, my input image is 2 to 4 by 2 to 4. And let's say my kernel is 64 by 64, right? So what's that going to do? That's going to produce one output, right? This is something we covered last week. It's going to have one output. And then this is going to go all the way around. So if it goes, let's say it brings over here, then this 64 by 64 all of this block is then going to produce one output. So you have a smaller size feature map, right? This is my smaller size feature map. So let's say I'm not exactly sure on what the dimensions would be. Maybe let's just find out. I should be able to do this, but sadly, I'm really bad. So let's say my input is 1 by 1, and this is just something you should also, like if you don't understand anything on what the output is, I always just code it up. So my output, I have one channel and my kernel size is 64. So my conv x dot shape would be 161 by 161. Okay, thanks. So this is just going to be 161 by 161. And then when you have your next convolution kernel, let's say I again have that massive convolution kernel, right? So all of that is then going to produce one output. But what this output, like what this output has seen is like it has seen all of the convolution kernel too, but all of these individual basically all of these individual activations or all of these individual outputs from the convolution had come from these massive receptive fields before, right? So they've seen, so in turn, this particular pixel in my conv2 has seen like a bigger part of conv1, like it would have seen something like that than just 64 by 64. So that's just what I wanted to make. Like that was the point that I wanted to make about receptive fields. Is like as we go down, the deeper layers of the convolution have seen just a bigger part of the image. I hope it is clear now, Durga. I mean, what's the, oh, sorry, thanks. This is, what's the necessity of training an architecture model from scratch? Why not initialize the model directly? Okay, that's a really good question. Generally, almost always you want to start with pre-trained weights. And you would train from scratch in particular in cases where the data set that you're working on is completely different from what you're trying to do. So for example, if you're working with cellular data or like histopathology, or like you're working with medical data, so there could be cases where ImageNet images are going to be very different with your with the medical images that you're trying to work on. And then in that case, you would want to start from scratch. But particularly for all of these tasks, like for PETS classification, for all of these different tasks, you would start with initialized weights that are trained on ImageNet. So I hope that answers the question. It's like most generally, you want to start with pre-trained weights. And then if your downstream data set or the task that you're trying to do is very different from ImageNet, that is when you would try starting and training an architecture from scratch. Okay, Naresh has answered this one for me, so thanks very much. Usually we want to use some sort of pre-training. Okay, that's been answered. Thanks very much. Oh, thanks for sharing this one. My Queensland AI Hub talk. So yes, if I go to this Queensland AI Hub talk, I won't play it, but you can see like I kind of, this is where my fast AI journey started, and these were it's not very clear, is it? And then in this talk, there was like all of these different papers that I was reading at the time, and then I just kind of shared my journey on how I started with one paper and then went on to all the other papers. It's really bad quality. I should reach out to Queensland AI Hub about that. Okay, leave that one with me. But basically, that was the talk. Thanks for sharing, Alan. So it will not be sufficient just to do convolutions. I hope this has been answered. Request to the host. Okay, that's something we can talk about later. Cool. So thanks for the great questions. And I hope now it's also clear about what's going on with colored images. So now I feel from this point forward, like there isn't a lot to teach, or there isn't a lot that's new in this chapter. But if you go back and you start looking at the chapter 13 convolutions, everything should be clear to you now. You shouldn't have even a single question about like, oh, what's happening over here, or like, why is this output of that particular shape? So have a think about all of that, and if there's any questions, then just reach out to me on the forums. Okay, so now from this point on, we're in 1.4. At this point, we're going to start looking at a simple baseline of convolutions. Then we're going to see and understand the training stability, or we're going to start looking at like, okay, how do we know that our network is stable and it's training nicely. And we're going to look at this one cycle training, and finally we're going to wrap up with batch norm. So these are the last 4 things for chapter 13. So we're just going to grab our MNIST data set. So MNIST is just 10 basically. MNIST is just basically 10 digits. So let me just create my data loaders and just show you the batch when that runs. Hopefully it won't take that long. Okay, so I've got like, this is what I have. Like my input data set is basically, we have 10 digits, which are 10-digit images of 4 is like, and the output labels are just what that digit is. So if you have an image of the input digit as 4, the label for that is 4. Or if you have an input digit of like handwritten digit 0, then the label that the model needs to classify is just 0. So in this case, you can just define a simple function called conv. What that does is that first it will create a convolution 2D, because in deep learning, everything is just convolution, batch norm, ReLU, pretty much. Right now, I haven't told you what batch norm is. So until now, what I want to say, okay, in deep learning, everything is convolution and ReLU. So you can see this is again what's happening here. You have your convolution 2D and you have ReLU. So what is nn.sequential? nn.sequential just means in PyTorch, it just says, okay, first, please apply convolution operation and then apply the ReLU operation. So if you want to check out, if there's any questions about what ReLU is, we've already discussed that this is an activation function, but this activation function basically for everything that's negative, it gives us the value of 0, and for everything positive, it gives us like a positive slope. So it just returns the positive value. So that's a non-linearity. So in this, I've just created a convolution function. It basically creates a convolution 2D followed by ReLU. So you can just apply that. So if I create something called conv, it says missing 2 input channels. So let's say input channels is 1 and 3. So see how that creates a convolution 2D. So that's my first, and then that creates a ReLU. So I could do something like ni nf for ni comma nf in zip. I'm just 1 3 7 9, and I could have my second list as 3 7 9 12. Let's see if that works. Oh, I need to close the zip. Does that work? Yeah, there we go. So now I have basically, like, I could create these bunch of convolutions, and I could put this all again in a sequential. I'm just like showing you some coding techniques that I could do. I think I need to pass in a star over here. Would that work? Yeah, there we go. So I can basically now, what I've done is like I was able to create 4 convolutions. Like this is why you want to define everything as functions. So just using like list comprehension in Python, I was able to create like a 4-layer deep convolution network. So this is what we're doing in this chapter, is like we're creating our own convolution. We're creating our own convolution networks from scratch. So what this does is, if you have an input image of 1 channel, it converts that to a 3-channel spatial feature map. Then it takes that 3-channel feature map and converts it to a 7-channel feature map. Then it takes that 7, goes to 9, and from 9 it goes to 12. And then it does that sequentially. So if let's say I'm going to call this my first, like this is not what the CNN that's been described in Fastbook. It's just a CNN that I've created now. So first CNN, and I'm just going to call it bad because it's really bad network architecture. And then my input is, let's say, 1 by 1 by 2 to 4 by 2 to 4, which is just saying I have a single image, 1-channel image. So let's see what the output is going to be. Actually, I should remove that. Cool. So then that gives me some output. So basically what's happened is, like, I would ask everybody to spend some time on why the output. So let me just paste this. Let me just take a snapshot of this and paste it here. And just say, why is the output that 1 by 12, basically. 1 by 12 by 14 by 14. So have a think, like this could be something that would be a nice exercise to check. Like based on the understanding of convolutions, this could be a nice exercise to just check, okay, why is this output 1 by 12 by 14 by 14? So have a go like layer by layer and check the outputs and then check this first CNN. Anyway, that's just something I think it will be helpful if I just added that code. So people copy paste. So anyway, just moving on, like that's why you're going to define things in functions. It's going to be really easy to define CNN architectures. And similarly, instead of like this pretty bad CNN that I had defined, in this book, you will see like this is a much nicer example. It goes from single channel to then 8 channels. The kernel size is 5. Then it goes from 8 channels to 16 channels, from 16 to 32, from 32 to 64. And finally, it goes from 64 channels to 10 channels. So you get your output that's 1 by 1 by 10. So you can just flatten it and you get 10 outputs. So with that being said, like FastAI also has a callback hook. So what you can do is you can pass in an activation stats callback. What that does, I will share very quickly in just a tick. So let me just run that. So if there's any questions on like what we've done so far, it's no magic. Like we just created a very, very simple CNN architecture. So this is our very first simple CNN that we have created from scratch, right? We just basically defined a convolution layer followed by ReLU. That was the one basic block. From that basic block, we just use that basic block to define like 4 or like 1, 2, 3, 4, 5 layer deep architecture. And then we can use that 5 layer deep architecture to train, like we can use this 5 layer deep architecture and we can try and train to classify digits. And what you can see is that the accuracy is 0.1. It's just 10% accurate, which is really, really bad. Okay. And now you're going to be, as deep learning practitioners, you're going to be in situations where you train a network and it doesn't train. You train a network and the accuracy that you expect is about 50%, but the accuracy that you get, or like the metric that you get, is so low. So in those cases, what you want to do, FastAI has this really cool trick, because we passed in a callback activation stats, right? What that does is it will start plotting the activations, or like the values, mean and standard deviation of these values at pretty much what the layer index that I pass in. So remember what I said? I said this is 5 layer deep. So 1, 2, 3, 4, and 5, right? So I'm just going to call this 1, 2, 3, 4, 5. And then what I'm doing is, like, remember, I would have an input image, right? So this input image would go all the way through my network to give me some output. So it would give me some output, correct? Like that's how this thing would work. Now, what I want to do is, like, I've created this network, but it's not training well. The accuracy that it's giving me is 10%, and that's a really bad accuracy. So what I want to do is I want to check, okay, hey image, when you went through layer 1, how was the mean and standard deviation? Then when you went to layer 2, what was the mean and standard deviation of the activations? What was after 3, what was after 4 and 5? So like I could actually plot these things, and FastAI really makes it easy. You can just say plot layer stats and you can pass in the layer index. So passing in layer index would pretty much plot the layer stats for layer 1. So you can see, if I plot the layer stats, you can see that the activations of like the mean is around minus 0.3, and the standard deviation is all over the place. And then most of my activations are close to 0, like 60% of my activations are close to 0. What does that mean? So activations, what is an activation? Activation is the output of a convolution layer. So these 3 graphs are telling me is, like, I had my first layer, right? I had my input, I passed it through this, and I get some output, right? It's going to be like, if I had 2 to 4 by 2 to 4, I'm going to say get an output of 2 to 2 by 2 to 2, and this is going to be, say, 32 channels, right? Now, what this graph is telling me, this graph is basically telling me that the mean, like all of these, remember, are just some values, right? These are all pixel values, right? They're like, it could be 0.7, 0.9, minus 1, 0.2, minus 0.3, or so on. Like these are just values. This is just an output of the convolution, correct? And because there was a value, so there's no negative values actually, they're all going to be 0, but there's some positive values. So what this graph is telling me is that it's telling me that my output, the mean of this output is minus 0.3. So there's definitely some negative values in there. Okay, forgive me for saying that there's no negative values in there. But where would the negative values be coming from if we have a value? Oh, okay. So the last one has activation false. Okay, that makes sense. All right. But the point is, like, out of all of these values, 60% of them are equal to 0. And that's not a good thing. Like, you don't want all your activations to be 0. It just means that the network isn't learning much. And you can see that by plotting this, by plotting layer stats of the first layer. And what that does is, if you plot the layer stats of the penultimate layer, or the second from the last layer, you can see that all of the activations are close to 0. So what does that mean? That means that this is a really, really bad network. It's not really learning much. And that is the reason why, like, as the image is going through our network, through each of the layers, what's happening is that initially, all of these are pixel values, right? They're like all are between values, say 0 to 255. And as this is going through the network, most of these activations, or most of the information, is being lost. Because by the end, you get out from your fifth layer, because it's going to go through first layer, then second, then third, then fourth, then fifth. By the time you reach out to your fifth layer, about 100%, because you can see over here, not 100% exactly, but like about 100%, there's a lot of those activations that have a value of 0. So that's really, really bad. And that's the reason why we get that bad an accuracy, which is 10%. So like, how do we solve this? Now we need to find ways on like how to solve this, how to make sure that our network is training. So one of those things that could be done is that we just increase the batch size. So we could try a bigger batch size. And what does that do? And these are, again, tricks that you should try when even on Cassava. Remember when we were talking about Cassava? Try increasing the batch size. If you're training on a batch size of 8, see what happens if you go on a batch size of 64. Or see what happens when you go on a batch size of 128. The reason why a higher batch size kind of stabilizes training is because the gradients are more accurate. So what that means is, remember how that looks like. You have a batch of images, right? So this is 2 to 4 by 2 to 4, but you have 64 such images, and this is what gets passed to my neural network, right? And if you increase the batch size to be like 512, as this goes through the network, so you pass your network, you get some output, you calculate the loss. So my first step is get some output. My second step is calculate the loss. And my third step is called loss.backward. So this is something I think we discussed in the first or the second chapter, but you're practically calculating the gradients and you're making a backward propagation. Remember, that's what we did in chapter 1. So let me see and find. I think it was intro. So anyway, so all I want to say is what happens is if you have a bigger batch size, then the gradients are more accurate because it's just easier for the network to train. And then when we increase the batch size and we check the percentage of near 0 for the penultimate layer, you can see that even though it's slightly better, it hasn't really done a lot of difference. So then the last thing, or like this, another thing that was introduced by Leslie Smith is this idea of one cycle training. And what this one cycle training does is, this is a really, really good time to start looking at papers. So sorry, one sec, let me just stop that. So this is a really, really good time to start looking at papers. So if I were you, what I would do is I would take the explanation that I will provide now, and then I would go to this paper, Superconvergence, and I would read all of it. Oh, sorry, I forgot archive is down. right now. I don't know why. But basically, what I would do this week is like, I would take this explanation of one cycle learning, and then I would start reading this paper. But the idea with one cycle learning, and we've already discussed this, is you start out with a really small learning rate, then you increase the learning rate to a maximum value, and then you decrease it. So you go down as you go in your epochs. So in your 0th epoch, to say if you're training for 100 epoch, you reach the highest value at the 10th epoch, and then you make it go sliding down. And this is the idea. Like, instead of basically until now, like, how is that different from until now? Until now, we have a constant learning rate. So if I have 100 epochs, we're just training with a constant learning rate of, say, 1e neg 3. But in this case, you start out with a really small learning rate of, say, 1e neg 5. Then you go to the highest value of 1e neg 3, which is 0.001. And then you go all the way down to, like, not negative, of course, but you go to like 1e neg 8 or something, or you go to a really small value. And the reason why this kind of learning rate, like, you start from small, then you increase it to the maximum, and then you make it go down. The reason why this is really good, or the reason why this will help increase convergence, or the reason why this will make the training more stable, is that if you start out with a learning rate like this, okay, remember our loss function looks just something like this, and there's all of these small, or you have these local minima. So you have something like that, okay? And then when you start with 1e neg 3, let's say I started here. So you jump around, you get this point, then you jump around, then you jump around, then you keep jumping around, you keep jumping around, you keep jumping around. But at this point, you wanted to stay here, right? You wanted to get to the lowest point. But because your learning rate is so high that the model will just keep jumping around, like your steps are too big, right? So instead, what you want to do is, if I take that same example, instead what you want to do is you start with small steps, and once you know you're headed in the right direction, because remember, that's what's happening. You start small learning rate, then you increase your learning rate, and then you decrease the learning rate. So once you start taking small steps in the direction, and you know you're headed downwards, then you start taking big steps. And what that does is, the reason why I have a big step here is because it will take you out of the local minimas. So you start taking a big step until you reach to your global minima, which is the lowest point in a loss curve. And then what happens is, like, once you've reached your highest learning rate, or you've reached like even a bigger learning rate, you start to reduce your learning rate, which means you start to reduce the step size, right? So what's that going to look like? Now you'd start taking smaller steps, right? Because that's what we're doing. We're reducing the learning rate. So you get to this point where the learning rate is so small that your step is practically like that small. So what we've done is, like, this way, the model is able to train a lot better and is able to reach the global minimum. Instead of like just jumping around the global minima, it's able to reach it. And this is what is one cycle training. So what I would do if I were you is, again, go back and read this paper. It's a really, really nice paper. It's a really nice read. And when you read this, it will expand your knowledge about learning rates. It will expand your knowledge about a lot of other things, about warm up, and it will introduce you. And not even if it expands, it will introduce you to like concepts or words like warm up or annealing. So these are words, or this is vocabulary that you would have never heard before. And then what will happen is, like, when you see a new word, you will probably Google it, and then that's the whole knowledge expansion, right? So once you start hitting those words or hitting those points where you don't know about them, this is where the real learning happens. So I would definitely recommend trying to read that. So let's try adding like one cycle learning to my network. So if I add one cycle learning, I just have to say fit one cycle instead of saying like fit before. So I was previously I was saying learn.fit, but now I can just say learn.fit one cycle. So if I train my model now, you can see Let's see what the accuracy is. Let's just wait literally 5 seconds. In that time, I will just have a look if there's any questions. Okay, no questions after this. So there's different types of initializing the weights on nn.conv2d. It is a good question, but I would just recommend you to go nn.conv2d, and I think there will be an answer about initialization over here. I think they do it using Keiminher initialization, if I'm not wrong. Let's see. There's definitely a parameter that lets you initialize them a certain way. In FastAI, I think it's Keiminher initialization. So that again is the learnable weights, the values of these. There we go. So in this case, I think it's a normal distribution. So you can definitely, I think I won't go into the details of initialization because that's not something we're covering today, but you can definitely have a look at here, but there's like all of those different initializations. So the answer is you can definitely customize it on however you want to. Okay. So where were we? Okay, we were just having a look at what the accuracy is. So you can see just by using this one cycle, now instead, like we didn't really change anything, right? We just started using this one cycle and we can see now our accuracy is 95%. So it's really important that our model trains stably and the activations remain stable. So now I can just see like this is exactly as I was saying, our learning rate starts from a really small value, goes to the top, and then goes back to a smaller value again. And now we can see the activation stats of the percentage near 0. It's much less than 1, so we're doing better, but again, it's still a large percentage of my activations are close to 0. So we might want to fix that. One thing that you'll see over here is like, okay, so I should just fix that. Just give me 1 second, please. I think I just need to rerun. No, this I did just rerun. So I can just rerun that, that, and that. Okay, so that's just that how many activations I have. Cool. So then in this case, there's this idea of the way this particular, there's this one of the FastAI students, what they did was they kind of developed a chart to look at how the distribution of my activation function looks like after each layers. So this is I will just go to the in-depth explanation and try and explain what's happening. Is there is this idea of called a colorful dimension. So what happens is basically, see how this is a normal distribution. If you have a higher value, it's represented by green. If you have a lower value, it's represented by red. So in this case, for a distribution like this one, you get the output, which looks like something at the bottom. So you have red, 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 green, 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 and red, 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 which just means that there's not a lot of negative values. So the number of negative values is low because it's all red, but there's a lot of values that are close to 0. And then there's less values that are close to really high positive values. So you could actually, so you can see like, I think there was a nice graph that explains how that looks like. Yes, over here. So you can see that for my normal distribution, if you plot it using this colorful dimension idea that was developed by a FastAI student, you can see it's like red, 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 green, and red, red. Similarly, if you have something like a biased, which is something where it peaks instead of at 0, it peaks at say minus 0.3 or 0.3, then in that case you can see there's a different, like the green, instead of being at 0, the green is over here. If the activations are well spread out, you can see that the values are much lighter. But if it's something like condensed, you can see like this is a really dark green as opposed to this green over here. That's because you have a lot more values at 0 in this case than over this case. So in this idea, what you have is like, you basically have, what you do with this colorful dimension plot is, I had 5 layers, right? Layer 1, 2, 3, and 4. Let's say 4 layers, right? So what you do is you have your input over here. then you get some output, so I'm going to call it O1, then you get some output, I'm going to call it O2, I'm going to get some output, I'm going to call it O3, and then finally O4. So what you could do is you could plot, like using this, you could plot the activation statistics, which we just plotted here, right? We can plot the means. So let's say the mean of O1 is like everything is near 0, so it's something like that, right? Something like that. For O2, pretty much everything is 0, so it's like a bar chart like that. For O3, everything is 0. So what you could do is like all of these could be converted into those colorful charts, which looks like this, like based on that, and then you could stack them together like horizontally, like because these are vertical bars, you could stack them together. And then if I do that, I get this really nice visualization that looks something like this, right? So what that means, yellow is again where the bulk of the activations are, or yellow or bright yellow is the point where the things are like it's a peak. So if I have a look at this first batch, I can see most of my values are 0, right? Then the model starts to learn. So my values are well spread out, like there's some positive values and then there's a lot of still 0 values until it suddenly drops, right? And then as I keep going forward, you can see there's still a lot of bright yellow values at the bottom. What that means is that my network isn't really learning well, right? There's still a lot of values that are 0, because remember, bright meant a higher number, and dark meant a lower number. So you can see there's still blue at the top and light green at the bottom, which just means there's a lot of values that are close to 0. Okay, so this picture shows a classic picture of bad training. So again, we want to make things more stable. And then the idea to make things more stable is to try and add batch normalization. So the next thing that you add to this is batch normalization. So I'm not going to tell you right now what batch normalization looks like, but let's see how that same chart looks like with batch normalization. Oh, it looks like this. This is perfect. So why is this perfect? Okay, in my first batch, I start with a lot of my values that are close to 0. See this bright yellow at the bottom? I'm starting with a lot of values that are close to 0. And then in my second batch, I'm going, okay, now there's like more values that are positive. Then as I'm going forward in my next layer, there's more values that are positive. Then I'm going as forward in my next layer, then there's more values that are positive. And in my next layer, there's more values that are positive until I reach this 5th or 6th batch, or like the 10th batch, where there's a nice even spread of the values. While still there's quite a number of values that are close to 0, but you can see now like this thing shows that now my network is learning. Instead of like my network learning like this, instead of like it's showing like the values are going from all of them being close to 0 to being spread out and then suddenly dropping again, and then suddenly dropping again, and then dropping again. Like this is an unstable learning chart. You can see from this like what happens after adding batch normalization is that my network becomes more stable. So I will now touch upon batch normalization, but before I do, let me just have a look if there's any questions. Are you going forward to the next model layer or the next mini batch? In this case, because we're plotting the activations for one layer, which means what you do is, remember, I have say 5 layers. And I have 1, 2, 3, say 100 batches. You first pass the first batch, you take this, you draw a vertical colorful dimension. You pass the second batch, you take this, you draw a colorful dimension. Third batch, take the output, colorful dimension. And then when you stack this all up, you get this image, right? So this is just, if I take this over here, if I take that there, then, because this is output for one layer, that's the first batch, second batch, third batch, fourth batch, and so on. And then from this particular thing, remember, if I have a look at the first batch, so I could maybe crop this part, right? I could just paste it here. What does that mean? This means that the activations look something like that. Remember? So if I have, that's my flat line, then that's how my activations would look like. Like it's a peak at, it starts to peak at 0 until that. That's how my activations look like at this point. And then if I go to this particular point, say, or that particular batch, then my activations look something like, because they're still up, so they look something like that, because it's still it's not as bright, which means the values aren't, there's not that many values in that particular place, but it's still a peak. But it's this is still better than this, right? That's the, I hope that answers the question, Kevin. So is it okay to remove those 0 values from the architecture for inference so that we get learn a model which predicts faster? Oh, we're not trying to, oh, sorry, I guess that's confusing. We're not trying to remove any 0 values. What this chart, like this, what that chart at the top was showing is like, as your image or as the activations go through your network, as they go from the first layer to the second layer to the third layer to the fourth layer, what happens is most of those activation values become 0. So it's called as zero propagation or something like that. I can't remember the technical term, but that just basically means like if most of your values are 0, then the gradients are 0. And when the gradients are 0, that just means you can't do a backward pass. And if you can't do a backward pass, that means your network isn't learning, right? So it's in everybody's best interest to have a mean 0 and standard deviation of 1, or like have that for the network to train stably. So what we want to do is we want to see our model. We want to see our model look like this, where there's an even spread. Like it starts, like even though in my first batch, a lot of the values are close to 0, then the activations are more spread out. Because that's my understanding of this image. It's like when that happens, that just means that now my network is learning and doing a much better job at learning than before. Okay, so what does batch norm do? So basically, remember, normalization is what? X minus mean divided by standard deviation in a way. So what this, again, not going too deeply into batch normalization because it's just like one paragraph that's been touched in Fastbook. So what that means is in batch normalization, you basically, as you go through the network, so as you go through the network, remember, where are we? This is what my network looked like, right? As I keep going through the network, I have now batch norm layers in between. So batch norm layers in between. And what this batch norm layer does is that it normalizes my output activations. So what's going to happen? You already know what it means to normalize an input image, right? If you have an input image and the values are all over the place, like 128 minus 100 or so on, when you normalize this, that just means it has a mean of 0 and standard deviation of 1, right? That's just what normalization does. So now you have really nice spread of activations here, like 0.5 minus 0.3 and so on. And you've normalized this whole image, so it's much easier for the model to train. But what the authors of this batch normalization said is like, instead of just normalizing the input images before feeding them to the network, why don't we apply batch normalization at every point after getting my output from the layers? So what this does is that it makes sure that my activations have a mean 0 and standard deviation of 1 as it propagates through the network. And what that does is it makes training a lot easier. So I will only touch that much when I talk about batch normalization. But basically, if you want to learn more, or looks like archive is back, if you want to learn more about batch normalization, I would say we go to this PDF and we start having a look at this paper. But otherwise, I've written a blog on group normalization. So if you go to this blog on group normalization, you will see an introduction to batch normalization. So you'll see what batch normalization does, what's the drawback of batch normalization. So if I think At this point, I will only cover batch normalization as much as it has been mentioned in the book, which is exactly what I've told you. But this is a good point then for everybody to pick up this basic idea that we want to normalize all our activations as we go through the network. But now this is a good point to like just increase and expand your understanding of batch norm. Go through the blog, go through the paper, ask questions on the forum, ask questions on Twitter, tag me on Twitter, or like, nudge me at forums, or nudge Jeremy, nudge Fast AI, tag a researcher. Like, these are the different things. If you don't find an answer, of course, I don't mean to say like spam anybody, but if you really have a genuine question that you can't find the answer of it, try tagging people, try asking them, try emailing researchers. So generally, lots of researchers provide their email. So if you generally have a really, really good question, which you cannot find, of course, the first step is to try and Google it. The next step is try and look at Stack Overflow, spend more time on the Fast AI forums. Most of the fast book related questions you will find on Fast AI forums, so I wouldn't be too worried. But I'm just saying this generally as we go down this journey. 2 years down the line, when you're reading a paper, like I was MDitor, and I was reading actually this is a true story for I think it was Convid. So I was reading this paper called Convid, which is improving vision transformers. We also did again, we also covered this at Weights and Biases, but I actually reached out to the author Stefane, and basically he was so nice that he got on a call on Zoom with me, and he helped me with the answer. And he basically helped me provide that answer. And then what that meant is like, then of course, all of that got converted into a blog post. So you can see when that comes up, if I go to this Convid blog post, which I wrote based on that, of course, then this blog post just starts with a credit to Stefano Diasoli for like getting on a call with me and helping me understand the Convid architecture. So if in your future, in your deep learning journeys, you do get stuck at a point where you really can't find the solution of it anywhere, try emailing the researchers, try looking on Twitter, or like all of these different things. But the main point that I want to highlight after like wrapping up this chapter 13 is that now is a good time to start reading research papers. Now is a good time to start experimenting, and now is a good time to start being more active on Twitter, and sharing those blog posts on Twitter, and like tagging people and all of that. So that's just what I'd like to say. Oh, looks like I've been so let's just see if there's any questions. Here's another blog post. Thanks very much for sharing. Let's click on that. Batch norm in 3 levels of understanding. There's a lot of content in batch norm that is true. So, okay, this is massive. But it looks like somebody's pointing that out. So yeah, there's lots of different blog posts that you find on all of these different ideas. So I would definitely recommend going through all of those different. Could you share some resources on how to do data pre-processing? Of course, but what kind of pre-processing, or like, what do you mean when you say data pre-processing? There's all of these different types of things. Do you mean normalization? All right, I guess this is where we will stop. And this is where we'll stop. So you can see, like, when we added batch normalization, we of course trained for more epochs, we got to that point of like 0.99 or 99% accuracy on the MNIST data set. So I guess for this week, what I would recommend everybody to do is, there were quite a few research papers that were mentioned in this chapter 13 convolutions. There was one by Leslie Smith, which is this superconvergence one. I think there was one about momentum. I haven't really told you what momentum is. That is something that will come, I guess, in chapter 16. So we will cover up momentum next week. But next week we're looking at ResNet. So next week then, let's join the paper reading group and cover that off as part of the paper reading group, and then you can definitely spend more time reading all of these different papers on batch norm. So now the onus is on everybody that's a part of Fastbook to build upon this platform and go about their ways on learning more from it. So with that being said, thanks everybody for joining me this week, and I will see you next week. Also, I'm flying to India this Saturday, so it is very possible that the timings for Fastbook from next week might change. I'll have to confirm, but just want to highlight that it is possible that the timings might change next week. So thanks for joining. See you next week.